So let's start with our warm-up problem. We have the integral from 0 to 1, integral x to 2 minus x squared, f of xy dy dx, and we're said it's equal to one of the following. Wait, what's happened? Well, if you look, this is dy dx, these are all dx dy. So it's like, oh, change order of integration. Okay, well, let's figure it out, right? So what do we have? Well, we can quickly sketch. We say, look, we have that from the outer integral, 0 less than or equal to x less than or equal to 1, and then the integral from the inside, x less than or equal to y less than or equal to 2 minus x squared. All right, so, well, y equals x. That's easy to sketch. 2 minus x squared, something like this. And where do they intersect? Well, if you plug in x equals 1, you get 1 and 1. So my picture's not great, but this is at 1 and 1. And currently, how are we slicing? Well, we're going from 0 to 1, top to bottom, right? So that's the current one. Now, if we're changing the order of integration, we're going to be going to horizontal slices, these kinds of slices. And what do we see right away? There's a change at y equals 1, which means, and when we say a change in bounding curve, which means it can't be any of these because it's going to have to be two integrals. So we've already knocked it down to two cases. Say, all right, what do we have? Well, down here, this integral has y going from 0 to 1, and x goes from 0 to y. So we need integral from 0 to 1, 0 to y. And we say, aha, that's doing it. This is going 0, 1, 0 to square root 2 minus y. That's not doing it. So the answer is D. Now, we should go ahead and finish verifying. What about here? Well, what happens? Y equals 2 minus x squared equals 2 minus y. X is the positive square root of 2 minus y because we're in positive x values. The negative square root of 2 minus y is on that side. And so from 1 to 2, we do go from 0 to the square root of 2 minus y. All right, so that is indeed the answer. Good, good. Nice warm-up, right? All right, well, thought for today. If we want to be able to make progress, we must learn how to handle being uncomfortable. Now, oftentimes, we say, but wait, I don't like being uncomfortable. I prefer being comfortable. Of course, everybody does. But you have to be careful. In order to really change, you have to go through challenges and trials. And you're going to be stuck. And you're going to be frustrated. Frustration is not a bad thing. Frustration is a typical sign and is often associated with things that come with growth and development. Now, there is a difference between being uncomfortable and being stuck. So don't be stuck. Keep trying to find ways to make progress, but be okay with saying, look, I'm not 100% happy, but I can keep moving forward. I can make progress. All right. Well, let's start with the real topic for today, which is we're doing integration, and we're going to start talking about different coordinates in integration. So we're going to do something which hopefully we're simple warm-up. We have the Cartesian coordinates, and we're very comfortable with how things happen in Cartesian coordinates. We describe our location using x and y. Well, but we also have polar coordinates. And polar coordinates acts a lot like radar. So what happens is you have the center, and you're saying, how does everything relate to the center? So you are pivoting through the center, so you're finding a direction. Once you found a direction, you're going a distance in that direction. So it's a combination of an angle, which really is a direction, and a distance. Now, you might say, well, wait, can we do integration in polar coordinates? And the answer is, why not? I mean, the coordinate system is really just a way of describing space, but when we talk about integration, it's a way of finding totals. It should not depend on our coordinate system insofar as what the answer is. However, it might make finding our answer easier. So why do we choose different coordinate systems? Well, we think about the region that we have. And it might be a region which is very agreeable, if you will say, to something Cartesian, or it's very agreeable to, say, polar. They might say, well, okay, Cartesian, that's great for what? It's great for rectangles. What about polar? Well, polar is really wonderful if you have circles at the origin. Circles at the origin, polar loves that. And so when you have a certain region that's very simple to describe in, say, polar, it makes sense to work in polar. There's also the situation where the function may be, again, complicated in the Cartesian system, but relatively simple in the polar coordinate system. And we'll see some examples as we go on. Now, as we think about what's happening, we're doing integration. There are three aspects for every integration problem you will ever encounter, and it's always these three. So the first thing is you have to think about, we're integrating over some region. How do we describe the region? Okay. The next thing is we have a function that we're trying to get the total of over that region. How do we express the function? Now the third thing is a little bit more subtle, and that's why I want to make sure we emphasize that, which is how are we breaking things into small parts? Okay, so let's focus our energy on this third part. So in Cartesian coordinates, when we think about breaking things into small parts, we say, well, our coordinate system involves x and y. So when we're perturbing our variables, we're saying, well, there's a little change in x, dx, and there's a little change in y, dy. And if we do that small perturbation, we get a little tiny rectangle. And we say, all right, now that's how we're breaking things up. So we're breaking things up by rectangles. So Cartesian, we're breaking up into rectangles. We'll make some notes here. Breaking into rectangles. All right. Well, given that that's the case, we say, well, how much is the area of this little rectangle? Well, we can figure that out. Dx dy or dy dx, either one. But the moral is we can find the area. Now, go to polar. And we're going to do the same thing. So recall, here we're perturbing our coordinate system. So we're perturbing x, perturbing y. So we want to perturb theta. So there's a small slice here. And we want to perturb r. So there's a small bit of change in theta. There's a small bit of change in r. And we say, okay, so here we have this part. Now this is a piece of a wedge. So we're breaking into pieces of wedges. Now it's not quite as romantic as saying pieces of rectangles, but that's all right. So now the question is, what can we say here about this area? What is it? Is it like dr d theta, or is there something perhaps a little different here? Now to answer that question, we're going to do a quick reminder. We have some space here, and we're going to do a little bit of geometry upstairs. All right. So recall that if you have a circle, and let's say the circle has radius capital R, and you have an angle here alpha, and the question we want to answer is, suppose we want to know how much of the area is in this slice of the circle. Well, we can find that by saying, look at the proportions. So the area that we're after, we'll call it A, is to the whole area, well, we know the area of a circle is pi r squared, as the angle at the center is to all the way around. Now a full revolution is 2 pi. Or we say, hey, that says that the area is equal to, if you multiply the pi across, the pi r squared across, the pi's cancel, you get 1/2 the angle, the radius squared. All right, now think about our picture. We have a wedge, so we have that the alpha is acting as d theta, but we're not taking the whole wedge, we're just taking a piece here. So this area is what? Well, our change in area, let's call it delta A actually, delta A for small change in area. Well, it's approximately, and we're going to have our 1/2, our change in theta. Okay, so there's our change in theta. And I'll explain why I'm choosing deltas and not d's in just a second here. And then let's find the whole wedge. And so that would be our r plus delta r squared. Subtract off this smaller part, r squared. Well, if you do a little bit of expanding here, that's r squared plus 2r delta r plus delta r squared minus r squared. And you're like, ah, ha ha, the r squareds cancel. And then you multiply through, say, look, we get 1/2 times 2 cancels, and you have this r, then you have delta r, delta theta, and then you have some other stuff, plus 1/2 times delta theta delta r quantity squared. Now, what's the punchline? The punchline is that this piece right here is too small in some sense. So in other words, as we get very small, this is the part that dominates. And so the great aha is to say the following, that hey, our dA here is r dr d theta. And that's the answer. Now, at this point, you're probably saying, what? Why is there an r here? Why do we need it? Now, I'm going to go through and argue in a couple of ways. First, let's think about the picture. So here, we've drawn this picture. Now, imagine that I were to move this in. So I can go this same length down here, and I say, well, look, compare this versus that. It's the same perturbation in theta, it's the same perturbation in r, but is it the same amount of area? Well, no. So in other words, the area grows the farther out you go. So there should be some factor of r that affects it. So that's one reason why intuitively we should get it. Now here's a second reason. When we're thinking about an area, intuitively it says, hey, you should have 2 measurements of distance. So notice, like for instance in Cartesian, we have a change in y. Well, that's a measurement in change in distance, change in x. Again, measurement in change in distance. Now, dr, that's a change in distance, so it's like a measurement of distance. R, again, it's a measurement of distance. So here we have 2 measurements of distance, but notice d theta, not a measurement of distance. So the moral here is that d theta, that's not helping you find it in an area. So that you need some sort of extra term here to compensate. And so that's why you need something like an r. In this case, it's exactly what you need. All right, good. So now, once you have this mindset, you're like, okay, so what do you do? You say, what's your description of your region? And you say, let's do it in terms of r and theta. And all right. What's the expression of your function? You say, no worries. Let's do it in terms of r and theta. And that's great. And then how do you break into small parts? And you just remember that dA is r dr d theta. And essentially, now you say, I've got everything set up, and you integrate. All right. So let's do a problem. First off, we won't worry about setting up an integral. We'll just say, hey, what does an integral look like? So it might look like the following. So essentially you say, hey, you've got r's and thetas. So suppose we wanted to find this. What do? Well, the answer is what you think you would do. And you might say, oh, well, what do I think I would do? And you would say, just integrate like you would have before. Oh, okay, yeah, that's what I was thinking. So you say, all right, you work from the inside. First, you integrate with respect to r. But before we integrate with respect to r, we say it makes sense to multiply that through. So integral 0 to pi, integral 0 to theta. It's always beneficial to really make what you're integrating as easy to integrate as possible, because integration is hard enough. So let's not make it harder. All right, now we'll start. Well, we're integrating with respect to r because we're in the inner layer. So the integral of pi r is 1/2 pi r squared. Integral of r squared, 1/3 r cubed. And now we're evaluating from r equals 0 to r equals theta. Well, nice thing when you plug in 0, you get 0. So we plug in theta. And we get the following. 0 to pi of 1/2 pi theta squared minus 1/3 theta cubed. All right, d theta. Well, now we integrate with respect to theta. Integral of theta squared, theta cubed over 3. And so it becomes 1/6 pi theta cubed. Integral of 1/3 theta cubed, well, we get theta to the 4th divided by 4. 1/12, and then we'll have theta to the 4th. And evaluate theta equals 0 to theta equals pi. Like, all right, well, plug in 0, you get 0. Plug in pi, what do you get? Well, you get 1/6 pi times pi cubed minus 1/12 pi to the 4th. And hey, that's really pi to the 4th. That's pi to the 4th. 1/6 minus 1/12 gives you 1/12 pi to the 4th. And there you go. Now, you might say, all right, what does this mean? Well, I mean, in some sense, the integral is just a quantity, but we can talk about what's going on. So if we think about our bounds, well, this tells us that the outer layer is theta, so 0 less than or equal to theta less than or equal to pi. And the inner layer is r, so that says 0 less than or equal to r less than or equal to theta. So we come here, we say, all right, so r equals 0 is the origin, because that's the only place you can go if you start at the origin and you go a distance of 0. Now, r equals theta starts out in the 0 direction at the origin, but quickly goes out and is this spiral. And so we're going from the origin out to the edge of the spiral. So you say, okay, well, great. So our region is this kind of interesting, curious one, which is not so easy to describe in our normal Cartesian coordinate system. But all right, great, that's fine. So now that's our region. We also can spot a couple of other things. We have this r dr d theta. This is our dA, which means that our function of theta and r is pi minus r. Now, you might say, okay, well, what is that telling us? Well, it's telling us that there's, it depends on interpretation, but a nice classical interpretation is to say, think about in terms of density. And what's happening? Well, it says that at the origin, r equals 0, it's very dense because you have pi. And as you move further out, the further out you are, the less dense you are. In fact, at the edge here, where here you have theta equals pi, and you get well, I should say r equals pi, you're zero density. So it's very dense object at the center, less dense out. And when you integrate density, it's like finding mass. So we can pull back and say, once you have an integral, you can sort of decompose the pieces, and then you can give interpretations as needed. All right, well, let's take a look. Here's a problem. Let R be the region in the first quadrant where 1 is less than or equal to x squared plus y squared, less than or equal to 9. And we're asked, find the integral over the region R, e to the x squared plus y squared dA. Now, let's suppose we put on our hats from the last time. We said, okay, what do we want to integrate with respect to y? Hopeless, hopeless. The y squared, e to the y squared, forget it. Never going to happen. All right, great. So that means we want to integrate with respect to x, right? No, also hopeless, hopeless. Oh my gosh, that's a double hopeless. That's not looking good. But we say, well, wait a second. There's some clues here. We see a couple of things. First off, this x squared plus y squared, that's a clue for polar. Now you might say, well, why would x squared plus y squared be a clue for polar? Well, what do you know about polar? We should do a quick recall. And if you recall polar, there are some basic facts, namely x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So this reduces down to some one term. Good. All right. Well, that's helpful. And another thing is, look at our region. So what do we have? We're in the first quadrant. X squared plus y squared equals 1. Well, that says we're the unit circle. So that's our lower bound. X squared plus y squared equals 9. Well, that's a circle of radius 3. All right, so that's this part. And so we're in between. Now, if you look at this, that would be a headache to do in rectangular coordinates. But in a system that would say, for instance, love circles, this would be very convenient for that. Well, so this is, when we see circles, we think are polar, right? Because this is a circle radius 3, so the outer layer is r equals 3, and the inner layer is r equals 1. So we say, nice. So this region we can describe in the following way, namely that theta goes from 0 to pi over 2, and r goes from 1 to 3. So simple description in terms of r and theta. Now, what about the dA part? Well, don't worry, we can handle that too. You say, look, we know about integration, and when we're doing an integration in our polar coordinate system, we say that dA, this is going to become r dr d theta. And it turns out sometimes that r can be very helpful. So, in our polar coordinate system, what does this all become? Well, we have integral, e to the x squared plus y squared is e to the r squared. dA is r dr d theta. Theta does what? 0 to pi over 2. R does what? 1 to 3. And that's our integral. And now we're ready to work the integral. And great. Now that doesn't seem like such a bad integral. It seems like one we can make progress on. And that's because we can make progress on it. And we actually can do one thing which may not seem intuitive at first, but notice, what do you see here in the bounds? What do these all have in common? These are all numbers. Okay, yeah, sure. What does that mean? Well, when you see all numbers, You can say, well, can I pull the functions apart? Function of r times function of theta, yes. Then we can do the trick that we did before, which says, oh, you can really turn this, instead of a double integral, a product of two single integrals. Now, initially, that doesn't seem like it should be true, but let me write it down. So we can pull out the theta integral, and then we can do the r integral. Now you might say, well, there's sort of two reactions. Either, of course you can, or no, that shouldn't work. Okay, so why might people say that shouldn't work? Well, notice when we talked about doing this before, we said, you need to be in a rectangle. Well, actually, what you didn't need to be is you needed really just to have that these were numbers. But if you think about it, what is a rectangle in polar coordinates? So you might say, well, that's not a rectangle, but we're not in Cartesian coordinates. We're in polar. And in polar, this is a rectangle. All right. Well, that aside, and again, if you prefer to say, hey, I'll just do one layer at a time, great, do it. You'll get the same answer. No problems. Life is good. We're all still friends. So the first integral, we can work that one out. This will become theta, and we're going to evaluate from 0 to pi over 2, which means that this will become pi over 2. Now for this integral, e to the x squared, hopeless. But e to the r squared, by itself hopeless, but with an r, hope. Why? So u equals r squared. Then du is 2r dr. Or if you like, a half du is r dr. So we have the pi over 2 coming from the first integral. Then we're going to have the integral of e to the u. R dr will become a 1/2 du, and then we update the bounds. These are currently r bounds. We've got to update them to u bounds. So if r equals 1, u equals 1. If r equals 3, u equals 9, 3 squared. Well, okay, we can integrate. 1/2 comes out, so that makes pi over 4. And we have e to the u, because the integral of e to the u is e to the u, evaluated from 1 to 9, which gives us pi over 4 times e to the power 9, subtract e to the power 1, which we just call e, and there we go. Okay, wonderful. We're able to do things, and we like doing things. Doing things is one of our favorite things. All right. Well, let's try another problem. Find the volume for the set of points between the surfaces z equals x squared and z equals 9 minus y squared. Okay, well, that's weird, because we look at this and say, all right, volume, I guess we can do that. We just have to integrate our height, right? So x, y, z. Now, z equals x squared is what? Well, if we think about what that looks like, z equals x squared, that would say we're in the xz plane, and there's just copying it left and right. So it's sort of at this trough going along the y-axis. All right, so there's that shape. Now, on the other hand, z equals 9 minus y squared. Well, that'll have a slightly different shape. And what will that look like? Well, you come here, and you go down. And then you're just going to move forward along the x-axis. So we have sort of two troughs, one going up and one going down. And then there's sort of something vaguely happening here where they overlap. Okay, so there's some shape here where they're overlapping. And it's not so clear what that shape looks like, but let's think about what's true. Now, we've got to extract some things here. So we say, okay, so if we want volume, well, we're going to integrate over our region R a height. Okay, now that seems a very reasonable formula. We say, all right, well, which one should be the one on the top? Well, in our case, the top, the larger one, is the 9 minus y squared, and the smaller one is the x squared. So the height would be 9 minus y squared, subtract x squared, or 9 minus x squared plus y squared. And now you're like, oh, I think I know where we're going with this one. Yeah. Okay, but we still have to go there. Okay, so now where? Well, what's our region? Okay, so our region, if we're looking for something between two surfaces and we don't have a region given, what we have to do is, where do the surfaces intersect? All right, so the intersection, what would that look like? Well, you would have to have that the x squared would have to equal 9 minus y squared, or x squared plus y squared equals 9, which means that if you think about it, it's saying, your shape is over this circle of radius 3. And so, oh, okay, so our region here, that would be x squared plus y squared less than or equal to 9. And now we're like, well, wait, that's an awesome shape in polar. So let's write everything in polar. After all, it's our new tool, and we should try to get the most out of it. Okay, so we're going to integrate. Let's do our function. 9 minus quantity x squared plus y squared becomes 9 minus r squared. All right, the dA, r dr d theta. So function dA. What about our bounds? Well, there's our region R. Where does theta go between? All the way around, 0 to 2 pi. Where does r go between? Well, it's a circle of radius 3, so we're always going out to the circle, so we're always going from 0 to 3. All right, so now we're ready. Well, again, notice we have nice bounds, numbers, and nice function, so we can do what we did in the last one, break it up into two pieces, 0 to 2 pi d theta, and 0 to 3, we'll multiply the r through, 9r minus r cubed dr. All right, well, the first integral, it becomes theta, evaluate 0 to 2 pi. And then the second integral, well, we integrate, we have 9 halves r squared minus 1/4 r to the 4th. And then we evaluate r equals 0 to r equals 3. All right, well, almost there. And to finish it off, we say, okay, so the first here, we plug in 0, we get 0, so we get 2 pi. And now, well, we have 3 squared, that's 9, times 9 over 2. That makes 81 over 2. And then we have here, we have what? We have 3 to the 4th, which is 81. 3 times 3 is 9. 9 times 9 is 81. So minus 81 over 4. Well, if we think about that, that's really 2 pi times 81 over 4. But I can cancel the 2. And so we end up with 81 over 2 pi. And there we go. We found it. We found our area. Woohoo! Nice! That's cool. And this is one of those problems when you look at it initially, there's nothing that says polar, but as you get into it, you say, oh, I'm seeing x squared plus y squared, I'm seeing circle, and when you start seeing these things, you say, polar. All right, well, let's try another problem. Okay, well, find the integral 1 to 2, integral 0 to square root 2x minus x squared, 1 over square root of x squared plus y squared, dy dx. All right, now this looks pretty hopeless, right? So let's think about this. Now, we know we're going to go polar just because that's the theme of the day. It's a polar kind of day. Is there any clue that polar might be helpful? Well, notice this 1 over square root of x squared plus y squared. What would be another way to write that? Well, if you think of square root of x squared plus y squared, in polar, x squared plus y squared becomes r squared. So this would become 1 over r. Oh, okay. Well, dy dx, this is your dA, and this would become your r dr d theta, which means that if we did convert this into polar, we'd have integral 1 over r times r cancels, and then we'd have dr d theta. So we literally would be integrating 1, and that's a great kind of thing to integrate. So that, at least in terms of this part, life is good. But what about the bounds? Okay, you have to think about those. Well, all right, so what do we have? We have some bounds here. Certainly, let's focus on these curves. Y equals 0, y equals square root 2x minus x squared. And if we think about that, well, let's square root 2x minus x squared. If you square that, you get y squared is equal to 2x minus x squared. Or you could say, well, that's really x squared minus 2x plus y squared equals 0. But then we put on our complete the square hats. So we'd add 1 to complete the squares. X minus 1 squared plus y squared equals 1. And we say, recognize. We know what this is. This looks like a circle, because it's a circle, where what we've done is we've moved the center to 1, and it has radius 1. All right, now because we're taking the y equals square root 2x minus x squared, it's the top half of the circle. And notice we're only interested in x between 1 and 2, which means our region that we are interested in working with is this region here. Okay, so this is our region R. All right. Well, that's great, but now we've got to figure out what's going on in terms of our parameters theta and r. Well, let's pick one of them. Let's start with theta. So say, well, in terms of theta, we're starting here, the positive x-axis, which is theta equals 0, and now you just keep pivoting until you run out of r. And we run out of r at that angle. So the question, what's this angle? Well, notice this point right here. It's at x equals 1, and it's also at y equals 1. So this angle, it's a familiar angle. It's pi over 4. All right, so that tells us our theta bounds. We're going from 0 to pi over 4. All right, now what about the r bounds? Okay, so for the r bounds, what do we do? Well, we always come from the center, and we just move out till we hit where we start, and we move to hit where we end. So we start at this line x equals 1. So do you put in 1? No, because remember, this is an r bound. So we're like, oh, so we've got to rewrite x equals 1 as r equals something. And then we remember, well, you know, x is r cosine theta. All right, we can write that better. X is r cosine theta. So if I want to solve for r, divide by cosine. 1 over cosine becomes secant. So our lower bound, the first curve that we hit coming out, is secant. What about this furthest bound out? Well, that's this curve, y equals square root of 2x minus x squared. Now, we can play with it, but I'm going to come and start over here. This becomes x squared plus y squared equals 2x. So I'm going to take the 1's out. What does x squared plus y squared become? R squared. What does 2x become? 2r cosine theta. Well, you can divide out by the r, and you get r as 2 cosine theta. So our outer layer is 2 cosine theta. So we're going from secant theta to 2 cosine theta, and that's describing our region. All right, now we cannot split this integral up because we see functions here, which is great. It's nice to be able to not be able to do everything. So what do we have? Well, when we integrate 1, we get r. And we're going to evaluate from r equals secant theta to r equals 2 cosine theta, d theta. Well, that's easy enough for us to plug in. That would be 2 cosine theta subtract secant theta d theta. And we can integrate. Integral of cosine, positive sine. Integral of secant, log secant plus tangent. And of course, we need to evaluate from theta equals 0 to theta equals pi over 4. All right, now when you plug in 0, sine of 0, 0. Tangent of 0 is also 0. Secant of 0 is 1. Log of 1 is 0. So we're going to get 0 when we plug in 0. That's good news. So we plug in pi over 4. So we get 2 times sine of pi fourths minus log secant pi fourths plus tangent of pi fourths. Now sine of pi fourths, that's root 2 over 2. Times 2 means you're going to get a root 2, square root of 2, minus log. Secant of pi fourths, that's 1 over cosine of pi fourths, and cosine pi fourths is root 2 over 2. When you flip it over, you get 2 over root 2, also known as square root of 2. Tangent of pi fourths is 1. So we end up with square root of 2 minus natural log square root of 2 plus 1. And there we go. There we go. And yeah. And if you think about it, say, well, it wasn't trivial, but it was doable. And initially, this looked bad. This looked hopeless. And so we were happy that we got to a place where it's like, aha, hope, hope. We like having some hope. All right, well, let's try another problem. Okay, this one, famous. All right, find the integral from negative infinity to positive infinity, e to the negative x squared. And you might say, e to the negative x squared, what? I never care about that curve. But no, I would say that among students, this is the curve they care about the most. And in a very real sense, they always ask, well, what about the curve? What's the curve going to look like? And the answer is, it actually is this curve. This is the curve. So e to the negative x squared, if you think about it, it gets largest at x equals 0. And then as x gets big, either in a positive or negative direction, it gets small. And so you have this shape. And this has a lovely name. This is called the bell curve, and this is heavily, heavily studied in statistics. And basically, statistics is built around understanding this curve. Okay, well, given how important this curve is, one thing we'd want to know is how much area there is underneath this curve. And all right, so we just have to integrate e to the negative x squared. So do we know the antiderivative of e to the negative x squared? No! Can we find it? No! Hopeless! Hopeless! Ah! I hate when things are hopeless. So what we'll do is we'll call this, let's call it our answer. We'll call it A for answer. And now what we're going to do is we're going to do something sneaky. We're not going to find A, we're going to find A squared, which is we're going to find two copies of this. So we'll have one integral, negative infinity to infinity, e to the negative x squared dx, and then we'll write it again. But just so we don't get confused, let's choose a different symbol, and well, why not? We'll choose y. Now the great aha. Remember how we talked about pulling integrals apart? We can also push them together. So we say, oh, well, this is like the integral from negative infinity to positive infinity, integral negative infinity to positive infinity of e to the negative x squared, e to the negative y squared, dx dy. Or if you like, negative infinity to positive infinity, negative infinity to positive infinity, e to the negative x squared plus y squared, because we can just put those together. When you have exponential functions, you add their exponents. And now we start seeing some bells in the back of our head going off. And we're like, hey, we know how to handle things with x squared plus y squared. In fact, we've seen a problem highly similar to this very recently. So our great aha is, let's switch to polar. So if we switch to polar, we say, okay, well, first off, what's our region? And our region is everything. Okay, well, that's a lot of region. And we say, okay, so let's, we'll figure our bounds out for everything. And then we get e to the minus r squared. That's the function. And then dx dy, this is your dA, r dr d theta. And now theta, well, we got to go in all directions, 0 to 2 pi. And then r got to go out all distances, 0 to infinity. And now we do the same thing that we did before. In the interest of time, I'm going to go through this at a bit of a pace here. So pull out the integral with the theta, and pull out the integral e to the minus r squared r dr. Now the first integral, that becomes theta, evaluated from 0 to 2 pi. The second integral, you're going to do the same trick we did earlier. We're going to let u equal negative r squared du times a half times a net minus is r dr. And so we end up with what? Well, we end up with minus 1/2 e to the u, and then evaluate that from 0 to minus infinity. Now, we're almost there. What do we get? And the answer is from the first part, 2 pi subtract 0 is 2 pi. From the second part, plug in minus infinity, goes away. Oh, nice. 0, plug in 0, e to 0 is 1, so minus a half, and we end up with pi. Ah, so our answer is pi. No, because follow it back. Our answer squared is pi, so we end up with a square root of pi. So a squared equals pi, meaning a equals square root of pi. And this is why in statistics you see that really weird, what does a pi have to do with statistics? It's because exactly of this integral. All right, we're basically out of time, But here's a quick problem you can think about. Let R be the region in the first quadrant above y equals 0, below y equals x, and satisfying 4 less than or equal to x squared plus y squared less than or equal to 36. Then the integral over our region of arc tangent y over x dA is one of these. You can pause to think about it for just a second. All right. Did you pause? Did you think about it? The answer, 1/2 pi squared. All right. Well, if you want to look, see the solution, you can look at the scanned in notes. But otherwise, that's it for today. And thank you, and see you again.